Hello, everyone. Thanks for coming to my talk today. My name is Seth Polson, and I'll be presenting our work, Auto-Generating Natural Language Proofs for Proof Education. My collaborators in this work are Matthew West and Talia Ringer, who are professors at the University of Illinois, where I'm a PhD student. Today, I'll be talking about education. So first, I'll talk about proof blocks, an educational tool that we've been using to teach students to write mathematical proofs. And then I'll be talking about how we want to leverage automated theorem provers, specifically COC, in order to improve our problem authoring process for writing problems in proof blocks. This is a screenshot of the proof blocks user interface. A student is shown a scrambled up lines of a proof, and they're given the opportunity to drag and drop them back into the correct order. Then they'll receive automatic feedback instantly from the computer about the correctness of the way they've arranged the lines of the proof. This is a great tool for education. We've done research showing that students can learn about mathematical proofs much more quickly in the early phases of learning using proof blocks than writing proofs from scratch themselves. And we've also shown that these are very valuable as test questions, as they give an accurate measurement of student knowledge. When the instructor writes one of these proofs, they simply have to write the lines of the proof and then specify the logical dependence relationships between the lines of the proof. And then the proof block software generates the user interface. Let's look into this in a little more detail. So here's an example of the same problem, but this time annotated with some more information. So as I stated, when the instructor writes the proof blocks problem, they specify the logical dependence between the lines of the proofs. And these logical dependencies imply a directed acyclic graph, which is the graph shown on the right. So in this proof, line 7 logically depends on 3 and 6, 3 depends on 2, 2 depends on 1, 6 on 5, and 5 on 4. So the autograder will recognize any topological sort of these lines of the proof as some correct solution to the proof and give student full credit for that proof. On the problem authoring side, this is the code that an instructor had to write to generate this question. This is a custom dialect of HTML that's understood by PrairieLearn, the learning system that proof blocks was first integrated into. The tag and depends attributes are how the instructor writing the problem specifies the logical dependence relations between lines of the proof. This has worked great for us so far for the most part. We've had multiple instructors write problems, and they're able to easily pick up the system simply by looking at a few examples and then writing some more on their own. However, there are a few drawbacks to this system. One of them is that the dependence graph between lines of the proof needs to be specified by hand by the instructor, and it's easy to make mistakes. Misspecifying the logical structure of the proof leads to students being frustrated that a correct proof that they input is not recognized as correct by the autograder. The solution to this so far is to have teaching assistants for the course manually try out the problem before putting it in front of the students. But this is a costly and still an error-prone process. Of course, because we're at the COC workshop, you all know what the solution to this is: theorem provers. So that's right. What we want to do is we want to be able to take a proof that's written in COC, and we want to be able to automatically generate the proof blocks HTML, which includes both this natural language representation of the proof, because we focus on informal proofs in our courses, and the dependency graph between the parts of the proof. Now I'm going to take a step back and give a brief overview of the history of translation of formal proofs to natural language proofs. I know I'm going to miss some systems that were built, but I'm just going to try to give a broad overview so we can kind of get the context for what we did. So the first attempts at translating formal proofs to natural language go as far back as the 70s with Daniel Chester, who had a system called Expound, which would take some first-order logic, formally defined proofs, and translate them into some sort of natural language. A little bit later, some researchers did a similar thing with COC, where they just took the calculus of constructions representation of a proof, and they just translated what was there literally straight into English. The generated proofs by these types of systems were correct English, but they're very verbose and not very pleasant to read, especially when they get longer. Because we want to put these auto-generated proofs in front of real beginners who have never even seen a proof before, we have a very high standard for the quality of natural language that we want to have generated. So this sort of thing wouldn't really cut it. Thankfully, there's been a lot of improvement since then. The next round of systems that sought to generate natural language from formal proofs would take into account some higher level knowledge, either by aggregating information across different parts of the proof terms or by using the tactics directly. The example shown here is another example from Koskoy, but later on, and when they had done some smarter things to combine parts of the calculus of constructions representation before generating the natural language. And so there's some improvements here in the readability. As I mentioned, other people took similar approaches and made similar systems for other theorem provers. More recently, Gensalium and Gowers took a completely different approach to solving the problem of generating natural language proofs. They decided that in order to generate really high quality natural language, what they needed to do was go all the way back to what tactics the prover is even allowed to use in the proof. Because oftentimes automated theorem provers will have tactics in them that manipulate proof terms in a way that a human wouldn't normally do if they were writing an informal proof by hand. So what Gensalium and Gowers did is they built their own custom theorem prover from scratch, and they only built tactics into the theorem prover that they thought corresponded to things that a human would do while proving a theorem naturally. And they were able to get some really high quality natural language proofs from their approach, such as the one here, which is a proof that the pre-image of an open set is a subset under a continuous function. The approach that we use is mostly inspired by that of Gensalium and Gowers. But we were frustrated that because they had a custom-built system, we would need to either build from scratch all of the mathematics that we were interested in writing proofs about, or else only use proofs from a very narrow subset of mathematics. So we wanted to be able to leverage a larger ecosystem such as Coq, where there's much more theory built up and a much stronger prover. But we also wanted to have the benefit of Gensalium and Gowers' prover, where they were able to get this really high quality natural language by restricting the set of tactics that they were allowing to use. Our solution was to build our natural language generator, which we called Robot 2, after Gensalium and Gowers' Robot 1, to build it as a Coq plugin so that it has access to all of the internals of Coq, the proof state, and everything it would need to generate really high quality natural language proofs, but also to take a stand and say, we're really only going to ever bother with proofs that only use tactics that could be translated to natural language in a good, pleasant way to make sure that we have very high quality natural language. So in this table, we show the correspondence between the tactics used by Gensalium and Gowers' prover and Coq tactics. And this correspondence allowed us to roughly re-implement what they had done, but within the Coq ecosystem, so that it can now be more easily extensible to cover more different kinds of proofs. So in the end, we have our prover, which we call Robot 2, which is a Coq plugin that outputs natural language proofs, but only allows tactics that have clear natural language translation. This is an example showing how our plugin works. First, we take a proof implemented in Coq. Then we instrument the proof with pre-explain and post-explain hooks, which are calls to our plugin. The reason we have both of these is because in order to translate tactics into natural language, you need to be aware for some of them about the proof state before the tactic is applied. And for some of them, you need to be aware of the proof state after the tactic is applied And for some of them, you need to be aware of both. So it makes the most sense to just instrument the code completely. And then in the cases where the tactic doesn't actually need to know the state either before or after, but only one of them, you just have a no-op. And this at the bottom is an example of the final natural language that's generated by our plugin. There's a lot of challenges that you run into when you're trying to generate natural language proofs from a theorem prover. And not all of these are expounded very clearly in the literature. So these are some snags that we ran into as we went through our process. One of them is decision procedures that are hiding behind tactics. These are things like Isabel's sledgehammer or Cox's auto tactics. It's really not clear how such a tactic should be translated into natural language. And even if you were able to translate the underlying logical steps that are happening behind it, it's not clear that it would be able to be explained in a way that a beginner could understand clearly. There's also the issue of the use of non-standard definitions. For example, in most introductory proof courses, we use the definition of divisibility, that a number is divisible by another number if you can find some integer to multiply the first number such that the product is the second number. However, many theorem prover standard libraries use a completely different definition of divisibility, either by defining it in terms of the modulus operator or the greatest common denominator or something else. Now, there's great reasons for this because defining divisibility in these different ways can have great advantages for things like automation and proving higher level theorems. But if you're trying to generate proofs that are understandable by beginners, it's just not ideal. Another issue is the excessive proof term manipulation that happens in some styles of theorem proving. An example of this is the arrow and colon operators in the widely used ssreflect library, which people use to manipulate and move around goals between the context and the goal. These are very useful for writing computerized proofs, but proofs that use these operators end up with very messy proof terms, and it's not clear how to translate these tactics into understandable English. So what's next? The next step for us is to also extract the logical dependence of the lines of the proof from Coq, so that we can have proof blocks autograde these proofs when students work on them. After that, we hope to expand the types of proofs that our plugin can support generating English language from. I'd like to say thank you so much for coming to my talk. I really hope you enjoyed it. If you want to learn more about proof blocks, visit proofblocks.org or visit prairielearn.org to learn more about PrairieLearn. To see and run the code for our Coq extension, visit github.com/SethPolson/robot2. And if you have any questions about any of my work, please contact me at sethp3@illinois.edu. Thank you.